Good morning, everybody. So today what we are going to do is we are going to continue with B trees, and we're going to dive into each deletion. So the whole idea behind B tree deletion is that we have to maintain the same rules that we had before with B tree insertion, which is that we need to make sure that all the keys are at the same level and that we maintain this minimum degree. So you're going to see where this minimum degree becomes really helpful in ensuring that we can maintain the balances without having to do significant traversals up and down the tree. So I just said all that. Okay, so at the end of the last lecture, so we had a B tree with a maximum degree of 4. And we said a minimum degree of 2. And the whole goal was to, I'm sorry, there we go. What we end up doing is that we ended up creating this particular tree. Now, if we delete 15 from here, well, we still maintain the integrity of the tree, right? But what's going to happen is, but what if we want to delete 10? So 10, we have this here in a B tree node that it is its own element, which means that its count is equal to 1. So what we have to consider is, well, if this is 0, then we have a problem. We have imbalance. We don't have anything in this here. So this is the first consideration we need to make about balancing mechanisms. What we do have is we know the largest value to the left. We know that there are multiple elements in this tree above here. And we know that we're going to have an empty key here. So we can run into some potential ideas. We could delete 10, violate the rule, but then we have 6 and 7. And one thing that we could do is we could move 7 down, right? And then if we wanted to move 6 up, we could do this. And then we could delete 6 from that tree. So what we're doing, let me go back and review these steps here, is we are going to delete 10, and we see that the count is now 0. We have a count up here of 2, and we have a count here of 2. So what this means is that we can perform a right kind of rotation. And this allows us to maintain the integrity of the tree, because when we move 6 up here, and we move 7 down here, the order is maintained, and the pointers point to the right place. So when we have up like so, we see that if we were to traverse the tree, we would still have 5 over here, then 6, then this would go to 7. That would be the end. We go to 11. Then we follow this and we hit 12 and 13. So all of the properties that we need for the B tree are maintained. Yeah. Remove the node? No, we cannot do that, because we would have a scenario in which, so we cannot have an empty leaf in the B tree at the bottom. So well, first of all, we cannot have any empty nodes in the tree at all. And the issue is, if we had, so the question that Tiani has posed is, well, let me find the specific slide where I have that scenario. So I have this scenario right here, right? If I have a pointer in a B tree and I have a next value, this means that I must have a value here. Otherwise, we would have traversals that go nowhere. We cannot have we cannot have an empty leaf, and we cannot delete it. We will have to do something called merge, which we're going to adjust later. What you're proposing is going to cause all kinds of problems later on, particularly with making sure that the balances come into play. But what you are going to encounter, and we'll encounter this in a deletion or two, is this idea of merging nodes. So the rules need to be when we combine two children and move everything over. So here we're performing a rotation. I want to walk through this one last time just so we're clear. What happened is we deleted 10 and the middle node here, 10 was called this the right. Here on the left, we have 2 and 0. So we would take the largest value and we would perform a rotation, which means 6 is going to be moved up and 7 is going to be moved down. And then 6 is going to be deleted from that old tree. So now if we want to delete 5, this is where deleting the previous node would have caused problems. Okay. So we need to maintain the leaf height, but we don't need to keep every leaf. We don't need to keep every leaf. The rule is that we only delete if we can move everything else up or we can merge the trees together. And so here's an example. If I'm deleting 5, then we suddenly have a scenario where I have 0 over here and 1 over here, right? If I'm in that scenario, well, I can potentially figure out a way to combine these together into a valid BTree node. The other crucial aspect is I still have to maintain everything that's going on over here on the right. So here's the way we would walk through this. And I'm going to walk through it and then I want to walk through it again just to make sure that we see the pattern. So what's going to happen is I have all of these values here. I know that 6 and 7 are less than 11. And I know that 5 is going to be gone. And so what's going to happen is I can move 11 over and just put 6 and 7 down here. And what I'm going to do is I can combine that into a node. And then, Tiani, to address your question, we can merge these together. And by merging them together, that is when we would want to be able to delete a node. But in order to delete a node, then we would need to move all of the other keys and pointers over. So here's how this process would work. I'd say, well, I'm going to move 11 over. I'm going to move back. I'm going to move 6 down and move 11 over. I'm going the wrong way. Move 6 down, move 11 over, and then these two nodes here, 6 and 7, can be combined into 1. And the reason why I need to combine them, we see that we have an empty value here between two valid pointers. So what's going to happen is, since I'm moving it to the left, I am going to combine these two BTree nodes into 1. And this is why we need to understand what the minimum degree is. So therefore, I make sure that when I combine these nodes together, that it doesn't overflow the BTree node. So what's going to happen is 6 and 7 are going to be combined, and then this pointer is going to be moved over 1 in order to maintain the tree. So there we go. So we can't have a pointer after an empty key, so we move 6 down. We move over 11. We see that 11 is now the only value in the root node. And then now I'm going to combine 6 and 7 together. Okay, so does everybody see that? And now I'm pointing to a null node. So what I'm going to do is I'm going to move this one over like so. And so now we have our valid BTree. Our valid BTree, we have 2 nodes to the left that are less than 11, and I'm sorry, 2 values in one node that are less than 11, and we have 2 values in one node that are greater than 11. And we have 2 pointers to the left and to the right that go through this together. So what I would like to do is I'm going to take us back here. So now we're going to delete 5, and I would like all of you to try to work through this and tell me what to do. So what are we going to do here? What's the first step? We are deleting 5. Phil, let me make sure that the chat's available as well. So what's the very first thing that I did when I wanted to delete 5? So if we have the first comment in the chat. We want to delete 5 and then move 6. So we're going to delete 5, and the thing that I wanted to ask for is kind of the stuff in the middle here. step in the middle is I now know that the count here is 0 and the count here is 1. So to the left and to the right. So now I know that I have an empty value and I have a count of 2 up here. So now I can see an imbalance. And that is where, let me make sure that I give credit to the student who got it right. So Brandon has correctly indicated that we now need, based on this condition, to move 6 over here. So let me get to that step. So now we've moved 6 over. So now we have 11 in the first element. So we've moved 11 over. So now what do we do? Yes. Yep, so the from class was 6 and 7, and Fang Kong has also correctly said we're going to merge 6 and 7 together. And we know this because we have an empty value, so now we're going to combine 6 and 7 together. And so now what is the next thing that I need to do in order to ensure that I have a proper B tree? What would be the last step? Yes. Correct, we need to move over this pointer in order to do that. So I give credit to move the pointer of 12 and 13 over, so Fang Kong is also correct there. So that is exactly what's happened. We have now moved this over and we now have the valid B tree. So good job. Does anybody have any questions before I continue? All right, so now I'm going to really throw things out here. Now let's try to delete 11. So here's the challenges that we're going to run into when we try to delete 11 from this. Well, deleting 11 is the root node, and we would not have anything in it. So does anybody have any theories as to what we would want to do here? Yes. Very good. We're now going to move. Yep, we're just going to move up, and then everything is good. Right? So that's exactly what we got going on here. Oh, but now we want to delete 7. So we're going to try the very first step of trying to move 6 up, but now we're going to run into a potential problem, right? We would move 6 up, but what we would see is that we have 0 and 2. So what do you think we might want to do here to maintain the balance? Yes. Yeah, we are. Well, that's not what's going to happen, but that's a good guess. Okay? But we're almost there. Yes. That is what's going to happen here. And the reason why, Tiana, so what you said is a really good guess. And if you actually programmed it such that I see that if I added these two together, I could put them all together. But we also have to account for a scenario in which I delete this, but I would have several elements remaining in this node. If I have a third element in there, then we have to do what we've just proposed, which is that we are going to move 12 up and then move 6 back. So would anybody like me to walk through that step again? Okay, so everybody understands that? Awesome. Okay, so now I want to delete 12, right? So first we try to move 6 up, and then we see that we have 1 and 0. So now we've reached we've guaranteed that we've added these together, and so now we can just merge them. So Tiani, this is when what you said is correct. And then deleting 6 would just move 13 over, and then deleting 13 would delete the node, and then we would have a merge. All right, so does anybody have any questions so far? Okay, so what I would like to do is go through a real advanced step where we're going to insert a bunch of values, and then we're going to delete all the values. And so this encounters pretty much every type of case you might encounter on an exam. On an exam, what I will do is I'll give you a set of insertions, and then I'll ask you to delete 2 elements, and then select the final B tree. But what do I want to do is I want to go over and we're going to delete them all so we can encounter all these cases and we can think about all the possible scenarios that we might encounter. So first we're going to insert 1, and then we're going to insert 10. So these two are relatively simple. So first, actually, let me go back to, we have a B tree with a maximum degree of 3 and a minimum degree of 1. So based on that, how many keys or values may I contain in the B tree node? With a maximum degree of 3. Okay, sorry, we have comments in the chat. So Luke Miller is correct, it is 2. So that means we start out and we create a node here with 2 value slots, so 2 key locations, and 3 pointers. So that's what the max degree is. So here we have 1, and then we insert 10. And so I want to insert 17 next. So what should I do? What do you think I should do here? Yeah, yes. Okay, so what we're going to do is we're going to split and rise, as Tiani has correctly said, and then 10 will be in the middle. 1 will be in a leaf on the left, and 17 will be in a leaf on the right. So far, so good. So when I say on the right, because we have multiple pointers, it's to the right of 10, and 1 is to the left of 10. So far, so good. Where's 4 going to go? To the right of 1, very good. All right, so I'm going to have to impose this someone besides Tiani rule. All right, so now I want to do 35. Where's 35 going to go? Yes. Very good, to the right of 17. So now I have 18. Where is 8? What's going to happen here? Let's walk through this together. So where would 18 initially go before we need to perform any operations? Yes. All right, so what we'd say is we would put it in the middle between 17 and 35. So it'd be in the middle there. And so what would this do, and what we're going to do in this scenario? Who else wants to give it a try? Yes. Okay, so what's going to happen is, yeah, that's exactly what's going to happen. So in the middle, what would happen is we would split, it would become 18, 17, and 35, like so. And then what's going to happen is, well, because this is not full and we're moving this up, 18 can now go here, and the previous pointer here can point at 17, and this one on the right can now point to 35. So that's why the solution to that step will be this. Does everybody see that? All right, so 22, where's 22 going to go? Yes. Absolutely right. So 22 is going to move over there, and then it's going to bump 35 over. So now we have 16. So where's 16 going to go? We'll try somebody over on this half of the room. Very good, exactly right. Yeah, just had to ask. You'll have the confidence and know what's up. All right, so now I want to insert 9. What's going to happen here? Yes. Very good. Very good. So it's going to become 4, 1, and then 9. So 4 would go up here, right? And so 4 is up here. So now what do we do? Very good. Absolutely right. So now what's going to happen is we're going to have 4 and 18 are going to be the children of 10. 18's pointers are still going to point to those two nodes with 16 and 17. And the other one's going to be 22 and 35. And then 4 is going to point to where we have 1 and 9 where we split it before. So now it's going to look like this. Okay. And then the last step is 7. So who wants to tell me where 7 is going to go? Somebody new. Yes. Absolutely right. It's going to take the place of 9 and move 9 over. So now we've gone through the full insertion steps. So now we want to delete 4. So we're going to delete 4. 4 is here. All right, so let me look at what's going on here in the chat. Can we go over inserting 9 again? Very good. So now we're here. So now we're going to insert 9. And so first of all, let me check, let me see who's asking. Okay, so Brandon, here's what's going to happen. We insert 9. So this is a multi-stage insertion. So 9 would be to the right of 4. And then what's going to happen is, because this is an overload, we're now going to split and rise. So that means we would have, just in this subtree, I'd have 4, 1, and 9. So that would be how the pointers would work. But when I rise 4 up, what's going to happen is it ends up in a BTree node that is already full. And so what's going to happen is I now need to evaluate this. So 4 would be on the left, 10 is going to be in the middle, and so what's going to happen is that subtree would be 10, 4, and 18. So in order to make this work, the pointers would be such that 4 would be pointing to these two, and then 18 would maintain the integrity and point to 16, 17, and 22, and 35. So then what would happen is, at the code level, that temporary node is being freed, and then we would have that final value. So let me go through this. And so we see that it's split, and 4 is going to rise up. It's going to become the left, and then because it's overflowing, 10 is going to rise up and make it look like that. All right, so Brandon, did that address your question? You're welcome. All right, and then 7 and 9 like so. So now we are deleting 4. So we have this situation where if we delete 4, that would just make an empty node, right? So let me walk you through the step of what would happen here, of what the code is going to do, and then how you can get the result. So what the code is going to do is, because it's very similar to a binary search tree in this way, remember when we were designing binary search tree and we were able to select between whether it was the largest value on the left or the smallest value on the right? So in this case, in the design of this particular BTree, and I kept it this way primarily because there are several visualization tools that'll help you practice these kind of problems, and almost all of them, and all the prominent ones that will come up on Google search, select it by going to the left first. So I wanted to make sure I chose it this way, so that way it would make your studies simpler. So what's going to happen is it's going to say, give me this value, the largest value on the left, for 1. And then it's going to bring 1 up here, but then it's going to go, oh, I got 0 and 2, right? So then what it's going to say is, well, now I'm going to move 7 up here and then 1 back down. So in the animation, that might look a little confusing, but the reason why is to get back to the design of the code. That's why it does that. Now, if we chose the smallest value on the right, what would happen is it would just delete and then move 7 up. We would move right 9 over, and that would be much simpler. But then we'd run into the other problem when we're trying to grab from the left. Does that make sense? So let me walk through the animation, and if there are any questions, please feel free to ask. So I'm moving 1 up because we have by default chosen the largest on the left. And then I realize that I have an empty node. So then what's going to happen is it's going to say, I'm going to move 7 up. I'm going to move right 9 over by 1, and then move 1 back down. Right, does that make sense? So now I've deleted 4. And now I want to try to delete 10. So now we have some interesting things going on here. So what do you think, based on my rambling there, what do you think the first step of this deletion process is going to be? Yes. He's going to move up 7? Why do we think 7? Small, so it's going to be the largest value on the left. And what is the largest value on, I see where you came to that conclusion. So if I go the largest value on the left, what is the actual largest value of that subtree? It would be 9. Very good. So that's what you're going to say. You're going to say 9 in the back? Yeah. So what's going to happen is the first step is going to say, well, I want to move 9 up. So 9, now I have an issue. This issue is that I now have a leaf that is empty. Oh, sorry. So when I recursively go up, what's going to happen is it's going to see that I have 1 and 7 here. So here's the interesting thing about how the B tree works, and it propagates up these changes, so that way when it reads it at the next recursive level, it can make a balancing decision. And the benefit of this is that we don't have to do what we did with AVL trees, where we had to perform all these recursions. What's going to happen is it's going to say, well, I'm going to combine 1 and 7, like so, and then I'm going to leave an empty node here. So does anybody have any theories as to why I want to do that, based on what I was just saying? Any, yes? Very good. So now when we move back up, when we get to the root, now we're evaluating, we can see like, oh, hey, I have a imbalance here, so now I need to do some sort of combination. So what's going to happen is it sees that 9, 18, and the left child we have an imbalance. Furthermore, we have one that's 0. So now we have 1, 1, and we can merge these. And so how we're going to do the merge? The way we're going to do the merge is I can have 9 and 18, and I'm going to have a pointer before and after each of them, right? 18 before still had pointers to 16, 17, and 22. Does everybody see that? And 9 should be pointing here. So when I'm recursing that up, what I'm going to know is I'm going to have a non-empty leaf. And then if I have a leaf over here, I mean a non-leaf here that's 0, a non-leaf here that's 1, and a non-leaf that's 1, and I combine those, what's going to happen is I can guarantee that when I combine these together, that I will maintain the height rule. And so 9 and 18 are going to be combined. And we're going to move that up, and then we propagate that last one up. And then if that's empty, then what's going to happen is the root is now just going to point to its first subchild, like so. Now, the other benefit of this is that in the tree, we had a root pointer, right? And if it's empty, if I just pass it to its first child, then it's just going to point to null, which is what we would want. And then we would free this pointer. So by doing it this way, we can also ensure that we're deleting everything properly when we finally would get an empty tree. Does that make sense? So to walk through this animation one last time, I will start here. We are deleting 10. So the first thing I'm doing is I'm grabbing the largest value on the left side and moving it up to the top. And then I see that I have a potential imbalance. I want to keep propagating up empty nodes, so that way eventually I can delete it. I see that I have a combination here of 1, 7, and empty. And you'll see that I'm going to merge 1 and 7, and then I'm going to propagate the empty node up. Like so. Then I'm going to compare empty 9 and 18. I'm going to merge 9 and 18 into a node, and then I'm going to propagate that empty node up. And then when I evaluate the root, the way the root will work is that the root will say, oh, you're empty? give me your first child. And that will be the result. So if it's empty and there's nothing else in there, and it says, give me your first child, it would point to null. And therefore, when we free that node, it will become a valid empty tree. In this case, since we have elements in here, it'll free that, and now we have a valid tree. Right, does everybody understand that? Okay, so now, I'm sorry, well, that's gonna happen is I'm gonna delete 18. So what do we think is gonna happen when I delete 18? This one's relatively simple. I'm gonna delete 18. What should happen? Yes. Yep, I'm gonna move 17 up into its place, just like that. So now we're gonna delete 16. So 16 would become empty, right? And so we have 2 and 0. So what do we think is going to end up happening here to preserve the balance? Who wants to take a stab at it? This is one of the very first ones that we did. Yes. Okay, so forgive me, that's not correct, but you are thinking on the right kind of path here. So we are deleting 18, right? I'm sorry, we're deleting 16. So 16 is on the right of 9. So let me, you in the back, what were you gonna say? You're gonna move up 7. So you're close, you're really close. We're gonna move up 7 and then move 9 down and 17 over. So what's gonna happen is we're gonna move up 7, move down 9, and now we have the preserved pointers and we've maintained the integrity of the tree. So Dr. Morrison, when he fills these things out, he's a major pain. Oh, got to delete 9 now, got to do the same thing. We're free. And then we have 1, 2, and 0. So now this is where things get to be a little more complex. So what's going to happen is we would move this one down because now we are empty over here and we have 2 over here. So this is where your idea that you were doing comes into play. Because this is empty and I have 1, and I have 2 over here, what I can do is I can take 22 and move it over this way, like so. All right, so I have a couple of comments in the chat, so let me see. Move 22 up to first, and 17 down, move 22 up, very good. So now what we're gonna do is we're gonna move 22 up to make this work. So that's the benefit, one of the benefits of the B tree is this particular step. So what I'd like to do is I'd like to go back to when we were deleting 16 and seeing the comparisons just to make sure it's clear. When we're deleting 16, that makes the node empty, and we have 2 to the left. So by default, we're checking left first. Excuse me. Thank you. And so then we move 7 up. Then I delete 9. Well, I only have 1 element to the left here. So this will become 1, 0. But then I can check over here for 2. Then I get the smallest value on the left, on the right, move 17 down and move 22 up. So this becomes this stage. So now I'm going to delete 22. So now when I delete 22, we have this scenario where I have 1, 1, and that's going to become 0. So what do we think is going to happen here? Yes? If the animation ever lets me do it. Did I delete 17 instead of 22? All right, so what's going to happen is it's going to move up, it's going to see these, and it's going to go left and then merge. So it's really close. So what's going to happen here, so I'm going to start at 22. So at 22, what's going to happen is this one's free, and then we have 1 and 1, right? So what's going to happen is by default, I'm going to try to do the left rotation first. So now what's going to happen is it's going to do 7 here. It's going to move 17 up. And then we're going to move this pointer over. So let me walk through the animation again. 17 is going to move up, then 7 is going to move down, and then both of these so 7 is going to be gone, then 17 is going to move over, and then the last part is we are going to then move the node. Okay. So now deleting 7 is relatively simple. We just get rid of it. So 17, we're going to delete the root. We have an empty root. We now see that our two values 1 and 1 are less than the full size of the BTree node. So now we can combine them together and merge. And then we delete 1 and then delete 35. Does anybody have any questions about this? All right, so what I would like to do is I'd like to spend the rest of the 15 minutes of lecture kind of quickly going through some example code and how this is working at the code level. So this merge, what we're going to do is at a lower level, we're getting the result of 12. And 12 is that number that's a scenario where we split 1, 7, and 9, and then 7 got raised. So we have to account for a scenario in which we are receiving an element and we need to merge these together. So at a lower level, 12 is split and raised, and we need these nodes to account for the required key distribution. And so what's going to happen is we are going to merge them because we know the degree. So this is kind of what I was hitting on in the animations. We need to know the value of the degree minus 1 needs to be the index value of the main node. And then we need to copy all the rest of those pointers over to make sure that we fill in the blanks. So let me show you, I have an animation on this next slide where I have the child and the sibling, and I have the index is 1, and the degree is 3 plus 1 divided by 2. And so what's going to happen is I'm going to check these values, make a duplicate of 18, and then I'm going to move 19 over. And then what's going to happen is you're going to see these pointers go there and there, and then everything else is going to get free. So this pointer would go to null. And now we have 12, 18, and 19, and all the rest of these are gone. So whatever was the child of 19 is preserved, and then these two were null pointers anyway, but now we don't even have the registers that we would need to store the pointers. So next we have to move all the keys after the index in the current node one step in order to fill in the gap created by moving those keys. So then after that, we would need to delete the sibling, kind of like what we did in the animation. So to do this, we have the sibling where we have 19, and then what's going to happen is you're going to delete 18. So 18 was initially up here, then we moved it down. Then we have to free the sibling after we've moved everything over. And now after we freed it and that pointer is pointing to null, what's going to happen is these two, whatever happened to be the children there, are preserved. And so these were initially null in the first place. So now we've gone from null to either null values or valid children. So the key thing is wherever 19 left and right children were pointing, we now have accounted for that in our updated BTree. Right, does anybody have any questions? So here is the first half of the merge method in BTree.h. So we create a child and a sibling pointer. We make sure that we have the index and the index plus 1. So it's that child and sibling. And then we get the keys of that specific index and we move it over. Then we iterate through and we're moving all those elements over like we need to. And then here what we're going to do is we're going to check to see if the child is a leaf. And if the child is a leaf, now what we're doing is we're getting those sibling pointers and pointing them to this current child. So that was that part of the animation where we moved over the pointers. That's what's going on in this code. And then We iterate through and we make sure that we update those keys. So now the second part of the code is then we move all the keys after the index one step before to fill in the gaps created. So that was the second half of the animation. And then we move the child pointers after index +1 in the current node over to ensure that we maintain the integrity. And since we deleted one from that particular node, we delete the number of keys from that particular pointer. So here we have child keys is plus equals sibling keys +1 because we're merging them together, and we moved one down. And then because we moved that down, the one that we're evaluating is that one that was at the root. And as a result, we moved it down, so therefore we want to delete that particular key's value by 1. Okay, does everybody understand? So the next part is we had scenarios where we wanted to borrow from previous and borrow from next, right? So borrow from previous is going from the left child, and then we have a borrow from next in order to make sure that we have it valid and working. So here what's going to happen is we borrow from the left sibling and fill in the child of the index. So the 7 is going to move up. We see that here we're deleting 10, and we're going to move 7 up. I'm sorry, we're not deleting 10. What we're going to do is we're going to borrow from 7. So 7 is going to move up, and we're going to see 10 is going to move down. So it's going to be 10, 12, and 18. Like so. And now, because we are moving 7 up, the crucial thing that we have to bear in mind is that 7's children need to be maintained in the BTree. So watch what happens again. We're going to see that 10 is going to be here, 12 and 18 are going to be here, but 18 was initially there, so these 2 pointers need to point there. This pointer needs to point there, and this pointer needs to point there, to the old right child of 7. So therefore, we have to maintain the integrity of the tree. Okay, does everybody see that? And so we need to create the pointers. We're going to be moving these over, doing this iteration. Just like we were showing, we were moving everything over by 1, and then we grabbed that last element. So from borrow from previous, and I apologize, I thought I had updated that particular. This says index equals 1, degree equals 3 plus 1 divided by 2, child and sibling. So in the same thing, we are going to move 18 over, 12, then we move this over and move that over. So we have that part. Then what's going to happen is 10 is going to be moved down. Then we fix that pointer. Yep, then we fix that pointer, there we go. And then 7 is going to be moved up, like so. And so that's how that code is going to work. And so for borrow from previous, we did the same thing where we create the child and siblings. We move all the keys over 1 step ahead, just like we did before. So this is going to be child, so key I plus 1 is equal to child of I. So in this case, when we had 12, 18, and nothing, I plus 1 and child of I, this means 18 gets moved over here and 12 gets moved over there. And we say if the child's not a leaf, then we start moving those pointers over by 1. And then we say child keys of 0 is equal to keys of index minus 1. So in the animation, index minus 1 was 0 in the root node, and that's when 10 moved down. So that happens here at this particular piece of code. And then if the child's not a leaf, then we would set the last child, here sibling num keys. We move that over. And then what's going to happen is we are going to, moving the key from the sibling to the parent reduces the number of keys. So we're going to update the number of keys there. And then we would increment the child's keys by 1, but then the siblings gets decremented by 1. So in this case, we borrowed from previous. So that one had 1 less key, and then the new sibling has 1 more key. So borrow from next, and forgive me, I'm just going to go a little faster, but this is the same kind of concept. We're now borrowing from next. So this is going to be, we're borrowing from the right. And we're going to see that all the pointers go up, 18 moves over, 19 is going to be up there, and all the pointers move. So I say go on the same spiel about how this works, and we see that in the more detailed animation that we are going to first duplicate 18, then we're going to move the pointer, then we're going to move 19 up. We're going to see that 20 and 21 are going to move to the left, and we're going to account for all of those pointers here, here, and here. And then these pointers would be free to move along as well. So that allows us to perform that last borrow method. And then borrow from next is essentially the same thing, just in reverse. And then filling is when we combine everything together. It helps us decide when to use borrow from previous and borrow from next. And so this is when we do these comparisons of the number of elements in each side. And so in this code, we say if the index is not equal to 0 and child pointers of the number of keys is equal to the degree, then we borrow from previous. Otherwise, if we don't have that, that means we don't have the elements to borrow from the left. So now we will need to borrow from the right. And then what's going to happen is if we borrow, if the index does not equal the number of keys, then we merge at that index. Otherwise, we merge at index -1 because we would be deleting those particular elements. Okay, so what I'd like to show you for the last couple of minutes of the lecture is a sample application that I wrote where I'm building a small database of students using the BTree. So I have this student class that I have built. I'm going to briefly show that to you. I'm going to use overloaded operators, and I'm going to be reading in from an Excel spreadsheet database. And so this is one of the common applications. So let me first show you. So it's student.h. I have a student ID, first, last, email, and their major. So kind of a flashback to what we were doing with polymorphism back in the day. So if you're building a database and you're using inheritance and polymorphism, you could use different classes to be able to use to build a good database based on the different types of B trees. So you could use different B trees for different classes of objects using inheritance and polymorphism. So this is a way to build a diverse database. So here I have operators, less than or equal to, greater than or equal to, and then I have a operator stream. And then in student.cpp, I have a constructor with the member initialization list, and I have a set ID where I'm using the this keyword. And here, even though it's not necessary because it's not inherited, I'm just using that as a way to review. And then I have an output operator. But now in student database.cpp, what I'm doing is I am reading an argument from the command line. And what I'm going to do is I'm going to create a B tree of students. And then I'm reading in a database from a specific file. And then what I'm going to do is while the database is in, I'm going to read in those arguments. So for a string, this is going all the way back to the first couple weeks of semester. I have a string, get line, and string strings. Remember string string, we use that to be able to check our inputs. And I'm reading that into a specific string here. So get line allows me to go to the database in and get the line and then convert this. In this case, line string stream happens to be, where's the variable? Oh yeah, inline. So I can do the same thing for string. I can do the same thing for integers and all the whole 9 yards. And then I can create a temp string and then insert it into the database. And the last thing I'm going to do, and so there's 1 minute left to go, I'm going to seek a specific ID, and then I'm going to use that method print found nodes that I wrote in, that I presented in the previous lecture. And then I'm going to set the ID for a specific value and then find that specific student. Now, what I'm going to have here is if I go up 1, you're going to see that I have a CSV file. And so I'm actually going to be using this and to read everything in there. If I was opening this in Excel, you would see these in different cells. And the way that CSVs work is they read into a specific comma. So the way that I'm reading string is working is I'm reading into the next comma, and this allows me to be able to put anything between in a space in the same cell. And so here I have 86 randomly generated names and emails. These are not real people. So now what I want to do is I want to run make student DB. And it's going to compile. And so in the executable, sorry, let me scroll up here. You're going to see that I run the executable and then I have students.csv as the file name. And so what I'm doing here is I'm saying seeking 86. And the way the tree has been balanced, it starts out at 32, 48, 64, 72, 76. So we see that there's a balance that allows us to be able to reduce the number of elements we have to traverse in order to find things. So to get back, so it's 11:15, so I'm going to conclude lecture after this. In order to, the benefit of the B tree is that we don't have the memory penalties that are incurred with a hash table, but we are able to find things really fast. And then this is why that B trees tend to dominate for data structures that are used in modern databases. So the last thing, seeking 10, is much closer to the top. All right, so last quick thing before I dismiss. I've posted the expectations for the memorandum and for the project proposal that's due on Sunday. If you have not heard back from your mentor, I believe that everybody who was lingering has been caught up. But if that's still not the case, please send me an email and I'll provide a friendly poke to get that going. And if they can't meet with you before Sunday, there's 2 groups where the conversation's happening on Sunday, then I'll grant a 1-day extension so you can complete everything. All right, so on that note, if nobody has any other questions, you're all dismissed and I will see you all on Friday.